The example 6. Example 6 is pretty darn important because it's going to give you a non-comprehensive list of strategies, or not list, but examples of strategies that we're going to be using for anti-differentiation. Because anti-differentiation is more about strategies and pattern recognition than it is really memorizing rules like it was for derivatives. There is no product rule, there is no quotient rule, there is no essential chain rule for integration. Now, this one here is where we left off yesterday, and I said you needed to know your power reducing identities. And it was asked this morning, hey, is there one place to go to have access to all the identities that we're responsible for, and maybe even more? And the answer is yes. The World Wide Web is replete with things like that, but you have to filter through the noise. So instead, if you go to your favorite website and you look up at the top of the page, it says Getting Ready, and they have appendixes. And the first one is pre-cal stuff to know cold. That means you got to know it like the back of your hand. If you are very intimate with the back of your hand, you need to know it that well. There it is. And I typed all this stuff up, and I only listed the trig identities, which is not a comprehensive list by any stretch of the imagination, but these are the ones that you need to know for the BC exam. Okay? So you got your reciprocal identities, you got your ratio identities, you got your family of PIDs, you got, of course, your double angle for sine and cosine, and, of course, down there at the bottom, the two that we went over again yesterday, the power-reducing identities. You don't need to know the names of them. You just need to know them and how to use them, and I guess when to use them too, right? And then there's some other stuff on there, some equations. There's your unit circle, blah, blah, blah. So good stuff on the top of the website there. There's a couple of appendices. There's one spleen down there at the bottom. Don't know what that is. But anyway, all right, let's get back to the strategies, because we did complete example D yesterday, which puts us on example E. So we are also kind of getting used to using different variables besides plain old x, and in this case we got z. The integral of z cubed times 3 minus 2z squared with respect to z. If we just walk up to it, we're like, hey, I spy a product. So you scan and you say, okay, it's just going to be the product rule for integration, the product rule for integration. Do we have that? No, we don't. And if I had it, I'd give it to you. But I cannot give what I do not have, and it does not exist. So we can't just take the integral of this and the integral of this and combine them. So there's got to be a way. So maybe we'll use a power-reducing identity. If we can reduce the power of the integral, then it would have less sway over us, and we can dominate it. I don't know. That's not how you use the power-reducing identities. There's no trig in here, so we can't do that. What about what else do we do? What about expanding or factoring? What else can we do? Split up terms in the numerator. Multiply by 7 over 7. 7 over 7. That's 1. No, what can we do, Raph? Yeah, we can expand it. And that's the strategy here. Yeah, it was real obvious to some of y'all, but I want to go ahead and run through kind of like a mental flow chart of some of the things we've already done. Expanding is one of the things you could do. Now, this is a reasonable exponent, so you would be expected to expand it. Maybe if it's a binomial squared, a trinomial squared, or a binomial cubed. But if that had been like to the 22nd power, then you're missing something, or someone is being very cruel to you. So I would just walk away and start a revolt, a revolution against that person. Well, we could do this one. So here we go. Do we distribute the z cubed first? No, I've seen people try that. Your dear Aunt Sally says, please excuse. So we do the parentheses and then the exponent. So z gets distributed later. And, of course, to expand a binomial squared quickly, we square, multiply, double, square. So we get 9. Multiply, you get negative 6z. Double it, you get negative 12z. And you square the last one, you get positive 4z squared. All still times dz at the back. And now we can distribute the z. So if you have multiple terms on your integrand, be sure to put them in parentheses. You get 9z cubed minus 12z to the 4th plus 4z to the what? 5th, not 6. Good. dz. And now we have 3 terms, and they all look like they're set up ready to go for the power rule. Pretty nice. So here we go. We'll add 1 and divide, add 1 and divide, add 1 and divide. So z to the cube becomes z to the fourth, and we divide by 4 and we get 9/4, which doesn't simplify, but that's okay. Minus, leave a space, z to the fourth plus 1 becomes z to the fifth. Divide by 5, you get 12/5. Doesn't simplify. Plus, leave a space, z to the fifth becomes z to the sixth. Divide by 6, you get 4/6. 2/3. Yeah, simplify as you go. And we're done. We're smiling. We're happy. Life is good. Plus c. Good, good, good. Plus c. Plus c. Plus c. And that's it. We're done. Factor it. Pull out a z to the fourth if you want. Pull out a 1 to the 60th power. 1 over 60 if you want. I don't know. We'll leave it like that. Okay? So expanding is now one of our little strategies algebraically for manipulating it, in addition to identities. All right, this one here, you walk up to it. What's up, F? Hey, I see a polynomial over a polynomial. I also see a quotient. Is there a Hody-High rule for integration? No. So I cannot just take the antiderivative of the top and the antiderivative of the bottom and then divide them. It doesn't work. So what to do, what to do, what to do? What? Oh, factor. Factoring is the exact opposite of what we did here. Don't do that. Are you telling me that the exact opposite strategy of one problem might be exactly what we need on another? Wow. Wow. Yeah. One person's kryptonite is another person's Red Bull. I don't know. I just make stuff up as I go. Factor. Here we go. Maybe it works the other way around. One person's Red Bull is another person's kryptonite. Yeah, yeah. It's called diminishing marginal returns. Don't drink like 12 Red Bulls back to 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 back. And you'll know what I mean. Okay. Here we go. We're going to factor the top. And let's see. It's a trinomial. It's not a perfect square trinomial, so maybe it factors into the product of two binomials of first degree. Maybe well, you're hoping for an x minus 7. So yeah, maybe you put that down first and you see if it works. And of course it does. Of course it does, because this is a design problem. Don't forget your dx at the end. Okay, so now what happens to your x minus 7? They divide out. No, don't do it yet. You're right, because you want to put parentheses around it first, and then that way we know you're not just dividing out the minus signs. And we're left with x plus 2 dx. Now, let's think about this function. There will be a time very soon where we're going to be handed a function, and we're going to be taking the integral on our own initiative. It's not going to be handed to us because it's going to mean something for that graph. If I factor out an x minus 7, I know that that function f has a what at x equals 7? A whole at, and we can actually find the ordered pair. It's at 7 comma what? Nine. Yeah. Remember, it would be the limit as x goes to 7 of this. When we factor out, we divide out, we plug back into what's left. Because the graph looks exactly like x plus 2 everywhere except at 7, where someone came in and swiped away the 0.79. All right, so now we can find the antiderivative, and it's pretty easy at this point. 1/2 x squared plus 2x plus c. Of course, don't use 7, right? Right. Now, there will be a time where we're actually going to be thinking of the integral as an area under a curve, and that's actually coming up today. If we have a hole in a graph and we want to find the area under the region, the hole, the removable point discontinuity, is actually not going to be a problem when we integrate. Okay? So that's kind of interesting. So the antiderivative works when you divide out the x minus 7. An asymptote could or could not. It depends on how quickly the curve goes to the asymptote. And we'll do those later on in the year. Those are called improper integrals. Yeah. All right. We are done with this section. So quiz tomorrow over anything from this section, including your list of strategies here. So any comments before we cut off the recording? Hi. Remember the Alamo? Vive la France. Hello, Mom. All right. Free Willie. No, free Stephen Avery.